Dear students, in this session we will discuss Chi-square goodness of fit test. We write chi-square as, we write it like this and read it as chi-square. We can use the procedure to perform a hypothesis test about distribution of a qualitative variable. Distribution of a qualitative or categorical variable. Qualitative or categorical variable. Also, discrete quantitative variables that has only finitely many possible values. Discrete quantitative variables taking only finite number of values. So, categorical qualitative variables and also quantitative. Discrete taking only finite number of values. Stated differently, we consider the case in which each element of the population is assigned to only one and only one of the several classes of categories. Chi-square goodness of test is applied if we can assign each element of the population into one of the several categories. And such a population is known as multinomial population. Multinomial population. So, chi-square goodness of fit test is applied to multinomial populations. The data used in this test are enumerative and they are in the form of counts. Data are in the form of counts or frequencies. The data used in the chi-square goodness of test is enumerative. They are in the form of counts or frequencies. Our actual observations may be on a nominal or a higher scale of observation. As an example, the number of people in a sample who fall into different categories such as age, sex, income, job classification, etc. We categorize age into various categories, sex into male and female, income, different categories, or different type of job, etc., etc. So, our data are in the form of counts or frequencies, maybe on a nominal or a higher scale of measurement. And chi-square goodness of test is used in these cases. Now, we can use chi-square goodness of test for categorical or qualitative variables, quantitative if they take only finite number of values, that is discrete quantitative variables. Then a population where we apply this test is multinomial data are in the form of counts or frequencies. Now let us first explain what are the steps in chi-square analysis. The first step is we hypothesize about the population stating H0 and H1. The first step is to hypothesize about the population, and I will explain how hypotheses are formulated about population later. So first step is to hypothesize about population stating H0 and H1. Second step is we compute frequencies of occurrence. Frequencies of occurrence of certain events that are expected under H0. Frequencies of occurrence of events expected under H0. Events expected under H0. The third step is we note the observed counts of data points. Observed counts of data points. Frequencies expected under H0 or counts expected under H0. Third step is we note the observed count falling into different cells, and this is frequencies expected under H0. We formulate H0 and H1. Second step is compute the frequencies of occurrence or expected frequencies. Third is the observed frequencies we note. We consider the difference between these two, observed and expected. We note or we calculate the difference between observed and expected frequencies or counts, and the difference leads us to compute the value of chi-square statistics. From these differences, that is from the differences between observed and expected frequencies or counts, we calculate the value of chi-square statistics. And let me give a definition to what is chi-square statistics. The statistics, that is the chi-square statistics, is equal to the squared difference between observed counts and expected counts. It is the difference, the squared difference between observed count and expected count in each cell divided by expected count summed over all cells. So chi-square is equal to sigma of OI minus EI square. I is equal to 1 to k divided by EM, or simply sigma O minus E square by E, if there is no confusion about I. So chi-square is the difference between observed and expected, the squared difference between observed and expected counts in each cell divided by expected count in the cell summed over all the cells. And this is the statistics used to test the goodness of fit of a sample data to what is known as an expected probability distribution that we will see. So this is the chi-square statistics. Always remember this, sigma O minus E square by E, sigma OI minus EI square by EI, I is equal to 1 to k. Now remember that in the binomial experiment we have studied, the number of successes is a random variable and the probability of success is a fixed number p. We have earlier discussed the binomial distribution by using the example of a lathe producing good pins in a sequence of pins. The number of good pins produced is a binomial variable with a probability p, and probability is a fixed number. As the number of trials n increases, as the number of trial n increases, distribution of the number of successes, distribution of the number of binomial successes approaches normal distribution. Or we will say that n, as n increases, this binomial distribution approaches normal distribution. This also we have discussed in the previous class. So the number of items falling in any of the several categories is a random variable as the number of trials increases. So if you increase the number of trials, as the number of trials increases, the number of items falling in any category is a random variable, and observed number of counts in any cell OI is thus normally distributed. Observed number of counts in any cell is thus a normal random variable. Remember this. In the binomial experiment, as the number of experiments increases, binomial distribution approaches normal distribution. And the number of items in any cell as n increases is a normally distributed random variable. Remember also that the square of several standard normal variables has chi-square distribution. This we have discussed. OI is normally distributed random variable. And remember this, if Zi is standard normal distribution, Zi square is chi-square with 1 degree of freedom, and sigma Zi square chi-square with k degree of freedom, where I is equal to 1 to k. This also we have considered earlier. That is, the sum of several squared standard normal variables has chi-square distribution. The sums here, the sums OI minus EI square by the sums OI minus EI square are standardized random variables that are squared. So each of these approaches a normal random variable, and the sum approaches a chi-square distribution as n becomes large. So this is the reason why we say that sigma OI minus EI square by EI is a chi-square variable, because it is the sum of standardized normal variables. So the steps are: formulate H0 and H1, calculate expected frequencies, note observed frequencies. Observed minus expected is a chi-square statistics. And this is from the fact that as the number of trials increases, a binomial distribution approaches a standard normal distribution. And from the properties, it is clear that chi-square, this quantity has chi-square distribution. Now, given these definitions, let us define what is a goodness of fit test. A goodness of fit test is a statistical test of how well our data supports an assumption about the distribution of a population or a random variable of interest. This test determines how well an assumed distribution fits the data. So, a chi-square goodness of test is a statistical test of how well our data supports an assumption about the distribution of a population or a random variable of interest, and the test determines how well an assumed distribution fits the data. As an example, we often make normality assumption about a random variable. So, a chi-square test can be used to test whether our data fits well to the normality assumption. Because chi-square test is concerned with testing how well our data fits an assumed distribution. If you assume that a population is normally distributed, and if you have data, you can use the data to determine how well your data fits the assumed normal distribution. And many other cases are also there. Now, we start our discussion of goodness of it with a simpler test, a test of goodness of it in the multinomial distribution. Goodness of it in the a test of goodness of it in the multinomial distribution. Multinomial distribution is a generalization of the binomial distribution to more than two possibilities. Binomial, only two possibilities, success or failure. Multinomial, more than two categories. And in the multinomial distribution, we have k greater than two possible outcomes. Multinomial distribution is a generalization of binomial distribution. Here we have k greater than two possible categories. And a data point falls only in one of the categories. K is equal to 1, 2, etc. n. And a particular data point falls only in one of the categories, and the probability that a data point will fall in a category is constant and is denoted by Pi, with the sigma Pi is equal to 1. Pi is the probability that a data point fall in a particular category. If the probabilities that the data point, the respondent, fall in any of the k categories is given as P1, P2, P3, etc. Say P4, let it be P5, 5 categories. And each data point fall in any of the 5 categories, and the probabilities of each data point falling into any of these categories is given as P1, P2, P3, P4 and P5. Then multinomial population distribution with these parameters and n, the number of pupil in the random sampling, specify the probability of any combination of cell counts. If P1, P2, P3, P4 and P5 are given, n is also given, you can calculate the probability of a data point falling into any of these categories. For example, if n is equal to say 100 counts of people, 100 counts, then the multinomial distribution gives us the probability that 10 people in category 1, 15 in category 2, 12 in category 3, 50 in category 4, 13 in category 5, total 100. Then we can calculate the probability that 10 people in category 1, 15 in category 2, 12 in 3, 50 in 4, 13 in 5, up to 100. When we have such a distribution, we may use the multinomial distribution to test how well our data fits the assumption of k fixed probabilities P1, P2, etc., Pk or P5 falling into k cells. But working with a multinomial population is difficult, so we use the chi-square test of goodness of fit when sample size is relatively large, or sample considerations allow us to use the chi-square test procedure. Now, a goodness of fit for a multinomial distribution is something like this. A multinomial test for goodness of fit. Multinomial, a goodness of test for multinomial distribution is H0. The probabilities of occurrence of events E1 to Ek are given by specified probabilities P1 to Pk. H1, probabilities of k events are not the Pi. Probabilities are not Pi stated in H0. H0, probabilities of events are given. H1, probabilities are not. Then the test statistics is chi-square, and this test statistics follows chi-square distribution for large enough sample size. This is the goodness of chi-square, goodness of fit test. And in the next class, we will explain these concepts with an example. Then only the points will become clear to you.